Now, before I leap in and do lots and lots of examples of proton NMR, we do need to go a little bit deeper than we did for the carbon NMR because of, again, the fact that we're not just looking at 1% of the nuclei, we're looking at 99% of the nuclei. Now, the spectrum on the previous page was what's called a low resolution spectrum. You might have noticed that the lines were rather broad. Those bands, those absorbances were rather broad, certainly compared to the carbon-13 spectra that we saw. Now, what that means that if we go to a higher resolution machine, we use a bigger magnet, which gives us bigger resolution of the different splittings, then we can actually break those big wide peaks into much more resolved ones. And when we do that for that chloroethane molecule that we just did on the previous slide, we don't see two broad humps. We see seven little spiky bits that resolve into two broad areas. This area here that's got 4 bits, and if you look at the pattern, you can vaguely pretend, and we're going to vaguely pretend, that the 2 peaks on the outside are about the same height and the 2 on the inside are about the same height. And if we took a little ruler to it, we'd see that this is 3 times what that one is. Then over here we have a group of 3 peaks that are pretty much in the ratio 1 to 2 to 1. Now, these groups here, of course, these 4 little peaks here, were that hump that we said was associated with the green hydrogens. Okay, now what we've got there is we've got 4 humps, 4-line quartet that is called, and that is associated with a hydrogen that is next to a carbon that has 3 hydrogens on it. And this is where people will often get confused because we're sort of muddling up issues here. This signal is due to the green hydrogens. It's split into 4 lines because the green hydrogens are next to 3 blue hydrogens. And then this signal here, that was of course due to the blue hydrogens, the CH3, it's split into 3, so-called triplet, because that hydrogen is on a carbon that is next to 2 hydrogens. Okay, and so we get the so-called N+1 rule, that when you're looking at a high resolution NMR spectrum, the signal for a particular hydrogen is going to be split into different signals based on not what it's doing, but what the carbon next to it is doing. And so what we have here is this carbon is next to 3 hydrogens, and so we get 3 + 1 or 4. And then this hydrogen on this carbon is next to a carbon that has 2 hydrogens, and so that splits into a signal that's got 3 bits, a triplet, because it's 2 + 1. Now that's really tough to get. Some people it clicks immediately, other people it clicks a little bit longer. So again, I keep emphasizing and emphasizing and emphasizing this N+1 rule as we go through. For some people, it can help to actually explain where the N+1 rule comes from. Where do these splittings come from that we see when we resolve our spectrum well enough? Well, in order to explain that, I'm going to go back to the whole model that I had at the start. There's your energy levels, and we're thinking about a proton attached to a carbon, and it's got a certain spin here because the magnetic field has been applied. So it's spinning here clockwise, and then you put in just the right amount of energy and it goes up here and spins anti-clockwise, but it needs that extra bit of energy because it's going against the magnetic field. Now, in order to make my life a little bit easier, I'm not going to draw this as spinning anymore, but what I'm going to do is I'm just going to use arrows. This is where this proton here, this hydrogen here, the up arrow says it's spinning clockwise, and then if we put up enough energy, then we will take this proton and it will no longer be spinning clockwise, but after that right amount of energy, it will be spinning anti-clockwise. So up arrow means spinning clockwise, that's with the field. Down arrow means spinning anti-clockwise against the field. Okay, so with the field, nice, against the field, nasty. Now, when we were looking at carbon, we were just focusing on the one carbon because, let's face it, it was only 1% of all the carbons in there, and the chance that any other carbons nearby would have any effect were very, very small. Now we're focusing on protons. 99% of the hydrogen atoms in a given molecule are going to be active, are going to be magnetically active, are going to be these spinnable protons. So let's think about a situation now in which our hydrogen of interest is bonded to a carbon that's bonded to a carbon that has a hydrogen on it itself. So in other words, we got one adjacent hydrogen, and this hydrogen itself is spinning, and it can be spinning with the field or it can be spinning against the field, and the assumption is that it's a 50-50 mixture because this hydrogen is not going to be affected by the field that made this hydrogen do all its stuff. Okay, so in other words, this hydrogen here can either see another hydrogen that's spinning the same as itself with the field, or it's spinning against the field. Now what this means is that there are now not just one new energy level that it can go to, but two energy levels it can go to. One in which this other adjacent hydrogen is with the field. Now with the field's good, so that's a little bit lower in energy. Or in which this adjacent hydrogen is going against the field. Now against the field is bad, so that's a higher energy. So because of the effect of this adjacent hydrogen here, well now we could see photons that take this proton up to here, this much energy, or we could see photons that take this proton from to this energy. Okay, in other words, there will be two absorbances associated with this photon because its original jump has been split by the one adjacent proton. So what we would see here for this proton is, because it's got one adjacent proton, is we would see a doublet. You'd have the jump up to the lower frequency, that's that one there, or the jump due to a higher frequency, that one there. Okay, so you get a so-called doublet when you have one adjacent hydrogen, because that one adjacent hydrogen provides two possible options. Is that adjacent hydrogen with the field or against the field? Now let's make it a little bit more complicated, and now think about a situation in which this hydrogen here, this is the one we're interested in, has not one adjacent hydrogens but two adjacent hydrogens. So here now we got this carbon next to the carbon that has our hydrogen of interest. It's got both a pink and a green. Now pink and green are equivalent, but I'm going to put them different colors just to make it clear what's going on. Okay, now just as we saw before, the pink here can be with the field or against the field, and the green can be with the field or against the field. So I hope you appreciate that there are now not two possibilities but four possibilities, except of course it doesn't quite work out exactly like that. Let's think of all the possibilities that we can have for these adjacent protons that are going to affect the hydrogen of interest. Well, the first possibility is that both pink and green can be with the field. Now that's good and good, which means it's very good. So this means we got this possibility here that's much, much nicer than the original option. Now let's think of one in which the pink is with the field, but the green is against the field. So that's a good and a bad. Well, a good and a bad just cancel each other out. So the energy of that possibility is just the same as the energy that would have been there if we had no adjacent protons. Now we got the next possibility, which is the pink being bad, but the green being good. So good and bad again, well, they cancel out, same energy. So we got two of those possibilities have the same energy. And then, of course, the last possibility, both really bad, horrible, naughty, and so that's the highest energy. So can you see now what we've got in terms of possible energy levels for this proton here? It's spinning away. You put in just the right amount of energy, and it will go to that level if both of these hydrogens are good, or it's spinning away and one of those is good and one of them is bad, so it goes to this level. But that's two types of situation in which this can happen. This is twice as likely to be the case as this one. Or of course you can have the high energy situation in which this one here is surrounded by two protons that are both bad, so it will have to absorb the photon to take it up to that energy. So there's three possibilities, right? Good and good, bad and bad, or good and bad. And of course the good and bad is twice as likely as the good and good or the bad and bad. So that's why when you have two adjacent hydrogens, we see a triplet that is in that 1 to 2 to 1 ratio, because this one down here, the least energy, is the good and the good. This one here is the bad and the bad, and this one here is either the good and the bad or the bad and good. Okay, did that make sense? I hope so. We can talk about it in a future Zoom session if you would like, but that's essentially why you get this splitting in the high resolution, because you can see the effects on the hydrogen of interest of the adjacent hydrogens, and because the adjacent hydrogens can either be with the field or against the field, you increase the number of possible energy levels to which this photon can jump.